All right, good morning. How is everyone? Good, good. All right, let's continue talking about AVL trees. And I want to do this by looking at some examples. So recall our basic setup. We're building binary search trees. We're doing the same insert algorithm we've been doing, which is, move down to a leaf and append to the left or right subtree. But as we do this, we're looking at the balance factor of each node. So balance factor is height of the left subtree minus the height of the right subtree. And starting from where we change the tree, we can move up and find a place where a balance factor is either bigger than 2 or less than minus 2. And if that happens, the tree is imbalanced at that point. And we can turn it back into a balanced tree by making 1 or 2 adjustments to the tree. And the nature of those adjustments can be determined by looking at the balance factors. So if we find a node with a balance factor of 2 and its left subtree has a balance factor of minus 1, then we are in what's called the left-right case. And we can make this change to get to a left-left case. If we have an imbalance of 2 and the left subtree has a balance factor of 1 or 0, we're in the left-left case, and we can do this adjustment to balance the tree. And if our imbalance is a negative 2, in either of these cases, we have a symmetric set of operations we perform to get back to a balanced tree. So I want to build a tree on paper and look at balance factors and apply these changes in a few cases just to get some experience with actually manipulating trees. And you might see a question on a test where I ask you to do something like this. So I suggest playing along, and let's do this interactively. So somebody give me a number to start with. We're going to build a tree by putting numbers into an initially empty tree. So let's start with a 17. Good choice. All right, we got a 17 in our tree. And both children have a height of minus 1, so the balance factor here is 0. So this is obviously a balanced tree. All right, and we've already got our next entry from someone, so let's put in a 42. So is this tree balanced or not? Yes, it is. The balance factor here is 0. The balance factor here is minus 1. The left subtree has a height of minus 1, right has a height of 0. So this is still balanced. All right, so then someone said let's add an 11. So we'll put an 11, that goes to the left of 17. The balance factor here will be 0. And now actually things got better at the root because the left and right subtrees have the same height, so this has a balance factor of 0. All right, so give me another number to add. $111. All right, so we started the root, moved to the right. There's 42, move to the right. There's 111. So this will have a factor of 0. 42 will have a balance factor of minus 1. What's the balance factor of the root going to be? Exactly. The left subtree has a height of 0. The right subtree has a height of 1. 0 minus 1 is minus 1. And we didn't change anything thing from this point of the tree on down, so this balance factor is the same. Any children under that would have the same balance factor. Alright, so this is still a balanced tree. Alright, so someone said let's add a 75. So it's bigger than 17, bigger than 42, smaller than 111. So 75 goes right here. Balance factor here is 0. What's the balance factor right here at the 111? That's 1. Left subtree has a height of 0, right has a height of -1. So that's a balance factor of 1. What about the 42? There we go. So the left subtree is null. That's a height of -1. The right subtree has a distance of 1 from the root. That's a height of 1. So -1 minus 1, that's a -2. So right there is our imbalance point. And at that point, I'm not going to bother calculating these balance factors up here. I'm just going to erase it so we don't fall in love with it. But this is a -2, 1, and 0. The left subtree has a height of -1. The right subtree has a height of 1. The left subtree has a height of 0. The right has a height of -1. 0 minus -1 is 1. That's how the 111 gets a height of 1, or a balance factor of 1. Does that make sense? Does that answer your question? So each balance factor of a node n, let me do this in pen. Balance factor of node n equals the height of n left minus the height of n right. So yeah, each balance factor is calculated like that. All right, so we have a -2, a 1, and a 0. What case are we in? Which of our 4 cases? Yeah, so we're looking at the balance factors. -2, right child is 1, left child of that is 0. That only matches the right-left case. Node has a balance factor of -2, and the right child has a balance factor of 1. Right, to be left-left, we need a balance factor of 2, and a left child with a balance factor of 1 or 0. So we're looking at this point where we first found an imbalance of 2 or -2. Since it's negative, we're going to be in either the right-left or the right-right, and the right child of this node tells us which of those 2 cases we're in. So this is a right-left imbalance. And let me redraw this so we can do the manipulation. So I'm only looking at this subtree. And in this subtree, we've got a 42, a 111, and a 75. This is a balance factor of 0, 1, and -2. and we want to apply this adjustment. So for the right-left case, we want to remap those. So let me label these according to how this picture is drawn. So the point where our imbalance is -2, that's what's called node 3. So I'm going to label that 3. It has no left subtree, so A is going to be null. Its right subtree is node 5. So this is node 5. Node 5's right subtree would be D, that's null. Node 5's left node is labeled 4. And 4's children are subtrees B and C, and those are null. So I'm going to put a note here. A, B, C, and D are all null. And now we're just going to apply what this picture of the algorithm says. To go from the right-left case to the right-right case, we basically we swap 4 and 5. Right? We're going to move 4 to be the right child of 3, and we're going to move 5 to be the right child of 4. And we don't have any subtrees A, B, C, or D, so we don't have to worry about those. So this is really just taking this and swapping the 4 and the 5, moving 5 to the right. In terms of rotation, the way I think of it is here's, here's our original 3, 5, 4, and we're just going to change it like that. Alright, so we take 5 and 4 and we turn it around, so we have 4 and 5. So the new tree, the root is still going to be 42. The right child is going to be node 4, which is 75. And the right child of 4 is going to be node 5, which is 111. So the 42, 111, 75 changed into this. And if we look at the balance factors, just for verification, they look like this. And that is the setup for the right-right case. Root has a balance of -2. Its right child is -1 or 0. That's a right-right case. And the labels are the same. Right? The root will be node 3. The right child is node 4. The right child of that is node 5. And the correction we make to that is to move 4 to be the root, put 3 on the left, put 5 on the right. So node 4 becomes the root, 3 becomes the left, and 5 becomes the right. So that's the process of balancing this subtree, 42, 111, 75, right? This should change into 75, 42, 111. Which means our original tree is going to look like this. 17 and 11, those are unchanged, but then this subtree gets replaced by 75, 42, 111. It's still a BST. Everything smaller than 17 is here, bigger is here. It's smaller than 75, this is bigger than 111. But if we look at the balance factors, it's a well-balanced tree. All right, Got another number? $199, perfect. Go to the right, go to the right. $199. All right, balance factor is 0. Height of -1, height of 0. This is -1. What's the balance factor here at the 75? All right. Let's back up. We got a question in chat. Said, before you added the 199, how did you know this balance factor was -1? So just looking at this tree, the left subtree is just this thing with a single node. That has a height of 0. And looking at the right subtree, that's this little 75, 42, 111. That has a height of 1. Subtract those. That's the balance factor at this node. So the height of the left subtree minus the height of the right subtree. So the 75 node, similar setup. The left subtree looks like this. That has a height of 0. The right subtree looks like this. That has a height of 1. So exactly the same calculation. The balance factor of this node is 0 minus 1. That's -1. This node, left and right subtrees are null, so that's got a balance factor of 0. But now, what's the balance factor of the 17? Yeah, that's a -2. So how do we know that? Looking at this tree, 17, the left child looks like this left subtree. That has a height of 0. The right subtree of 17 is this. And this has a height of 2. Right? Maximum number of hops from the root to a leaf node is 1, 2. So left subtree has a height of 0, right subtree has a height of 2. The difference is -2. That's the balance factor. Right, so we're just going to use this formula again and again. The balance factor of a node is the height of the left subtree minus the height of the right. And on these heights, you get really good at knowing what the height of a tree is, because we do this calculation so many times. And just remember, a null tree has a height of -1. A tree with just a root has a height of 0. A tree that looks like this has a height of 1. So it's the number of hops from the root to the deepest node. All right, so we've hit a point where our tree is unbalanced again. And which case are we in now? Yep, this is the right case. Imbalance factor of -2 means it's one of these two cases, and the right subtree has a balance factor of -1 at its root. That's a right case. So let me label our pieces of our tree like we did before. This is node 3, that's where the imbalance is. This is subtree A. I knew I was going to run out. This is subtree A. This is node 4. This is subtree B. This is node 5. This is subtree D. And C is null. And even though D is just one node, it could be a whole big long tree with a bunch of nodes, right? And this is the root of it. But that tree gets moved around as an entire entity. We don't do anything inside that tree, so it doesn't matter if this is just one node or there's other stuff over here. That whole structure will just get picked up and moved. And so our rotation algorithm says we should turn this into the following. Node 4 should become the root. All right, so node 4, that's our 75. That should become the root. Node 3 should go on the left. Well, that's our 17. Node 5, which is 111, that should go on the right. Subtree A goes to the left of node 3, so that's our 11 and whatever came underneath that. Subtree B should go to the right of 3, well, that's our 42. So that goes to the right. Subtree C is null, so we don't have to worry about that. And subtree D goes to the right of 5. That doesn't change. That started off on the right of 5 anyway. So the right of 5, that's going to be our 199. And so if we find balance factors here, these all have 0. This is 0. This is 0. This is -1 minus 0 will be -1. And what's the balance factor at the root? That's perfectly balanced. Subtree has a height of 1. Subtree has a height of 1. And it's still a BST. You can confirm that everything, you know, is in the right side of the root, the proper side of the root. Yeah, this would be fun PA6. Or an ODP, right, if it's due tomorrow. All right, so this is the whole AVL algorithm. Basically, you calculate balance factors starting from where you made a change. For example, where you insert, you can work your way up. And if you find an imbalance, 2 or -2, identify which of your 4 cases you have, and make either 1 or 2 adjustments to move into this balanced case. And we're not going to prove that this works. You can do that. In an algorithms course, you would do that, for example. You'd go through and you'd look at these steps and confirm that after you do this, you end up not only with these balance factors, but the rest of the tree will be balanced as well. And confirming that this is a BST, we did that yesterday, right? You can just traverse these and see that your sort order hasn't changed from the original case. But that's, you know, like an algorithms course, a correctness of algorithms unit, and that's a fair bit of work. And imagine being the people who come up with this the first time, right? And trying to know if this is valid or not. But it's a nice algorithm. It's pretty low level of effort, right? These are pretty simple operations. And as long as you do this each time that you change the tree, your tree remains balanced. Now, if you insert 2 nodes before you do this, you might find a case where you have an imbalance of, say, 3, right? And this will not help you. This has got to be done after each insert or delete. Otherwise, your tree may be too unbalanced to correct with just 1 or 2 rotations. Does that make basic sense? So let's look at some sample code. So here's some sample code from a tree assignment I gave a few years ago. Similar to what you did in PA4, but this was just a binary tree of integers, so instead of license plates. But let's just take a quick look through here. So main program, right? So this was similar setup, right? You run your code, and you can type in simple commands to examine your tree, insert, delete, search, and so on. So give a welcome message, tell them how to get help, call fgets to read a line of input, and then if you want to insert a number, you just type a number and it automatically inserts it. So kind of like what we did in earlier PA. So how do I know if they just typed a number? Let's scan their input as a %d and see if scan returns a 1. If it does, you know what they typed in was an integer. So if scan returns a 1, well, scan's done two things. One, it's told me they had an integer, and it's stored that integer in this variable num. So let's search the tree and see if num's already in there, and if it is, give them an error message, say this is already in the tree. Otherwise, we'll go ahead and insert it. So that takes care of inserting if they type a number. Otherwise, they presumably typed a simple command. So now I switch on the first character of their input, and if it's an X, that means I want to look at the tree, so I call an examine function, which does different traversals and so on and so forth. If they typed a question mark, I give them a help message, which is my usage function. If they typed an S, then they're searching for a number. So call scanf again and search for the pattern S followed by an integer. And if that returns a 1, then scanf is telling me, yes, they did type S followed by an integer, and that integer is in this variable num. So I'll go ahead and I'll call search with that number, save the result in a variable, and if it's not null, I can tell them it's found, otherwise it's not found. If scanf doesn't return a 1, but they started with an S, that's a syntax error. So I can print a message, S should be followed by a number. And D is delete, exactly the same thing, except you end up calling delete instead of just searching. Right? Make sure the number is in the tree and then delete it. And then Q to quit, we release the memory and we return anything else, tell them how to get help. And we've done this a number of times now, but this is another example of why I'm suggesting that you use fgets and scanf instead of just scanf, right? Because for example, I don't know what they're going to type in. I don't know if they're typing a number, a search followed by a number, a bogus command, right? But I'm ingesting once. This reads one line of input from the user and it stores it in memory. And now I can chow on that memory 20 different ways if I want. I can scan it to see if it's an integer. If it's not, I can look at the first character of it. If the first character is an S, I can scan it again to see if it's an S followed by an integer. Right? I can keep reprocessing this however many different ways I want because it's stored in memory. Now, if I try to do this with just scanf, every time I call scanf, I also read in input. And this is why you either lose input or you go into infinite loops so easily when you use scanf. So this is breaking it up. This is ingesting a line from the user, and then all of this is just processing it, parsing it a bunch of different ways. All right, so a lot of this stuff is boilerplate. We looked at deletion last week, and insertion is straightforward, but I've made one tweak on it. So same as before, if your tree is empty, make a new node, return that. That's easy. And we know if we're starting with an empty tree, that the new tree will have one node, and that's going to be balanced because it just has a root. Yeah, switches are useful. They don't always work for you, but sometimes they do, and in those cases, it can make your code a little easier to develop. All right, so if the tree is empty to begin with, we just make a new node. Same business as usual. Otherwise, if the number we're inserting is smaller than the root, we want to insert on the left. So set the root left equal to the return from insert. And now there's one extra statement here, which is adjust the root. So adjust is a function that's going to basically do this stuff. I can pass it in a root, and it will see if it's in one of these cases and make adjustments to the tree accordingly. And it'll return the potentially new root of the tree. And I'll set that equal to root. So this is really all I have to add to keep my tree balanced. When I insert at the very end, I'll just call adjust. And up here in my delete code, after I delete, at each point where I finally do my deletion, I'll just call adjust. Alright, so let's look at the adjustment code. So this is the balance factor code. And this is embarrassingly straightforward to write if you know the definition of balance, which is basically the height of the left subtree minus the height of the right subtree. And when you have recursion, you almost always want a base case, and my base case here is if you're checking the balance factor of an empty tree, I'm just going to return 0. Because I know an empty tree, it has no children, right? I'm just going to call that balanced and say the balance factor is 0. Alright, so how do we adjust a tree with a given root? And I don't think this ever gets called, but if someone tries to adjust a null tree, I'm just going to return null because there's nothing to do. But basically we've got 4 cases. So I'll compute the balance factor of the root and the balance factor of the root's left child. And if the balance factor of the root is 2 and the balance factor of the left child is -1, I'm in my left-right case. And what do? I call this function called left-right. And the purpose of left-right is to take a tree that looks like this and change it into a tree that looks like that. And after I do that, I check to see if the balance factor of the root is still 2. And if it is, then I call my left-left function, which will change this tree into that one. And if I started off in a left-left case, then this first if statement wouldn't have fired, and now I'd be seeing a balance factor of 2. I would know that this left subtree has a balance factor of 1 or 0. Because it's got to be 1 minus 1 or 0. So this will apply the left-left adjustment. And then, 2 other conditions, only one of these will fire. Either the balance factor was 2 or -2. But if the balance factor of the root was -2 and the root's right child had a balance factor of 1, that's a right-left case. So I call my right-left function. And if the balance factor of the root is -2, then I'm in the right-right case, so I call right-right. So that's looking at the balance factors, right? This calculates the balance factors. This uses the balance factors to decide what kind of adjustment to make. And then all that's left is writing the actual adjustment code. So this is kind of a top-down methodology, right? So what does the left-right function look like, for example? It's supposed to take this structure and turn it into that structure. So I've repeated the symbolic representation of this picture, which was originally from Wikipedia. So for our left-right case, we can label our nodes and subtrees like this, A, 4, B, C, and we want to turn our tree into something that looks like this. Well, how do we do that? If we have nodes that are labeled the way that I, labeled and circled them on paper, right? This basically, well, the root is still going to be node 5. Node 5's right child is still going to be D. But node 5's left child should become 3. 3's left child will stay the same, but 3's right child should become node 4. Node 4's right child is still C, but node 4's left child should now become B. So let's write those down. So to go from left right to left left, 5 is still the root, 5's right child is still D, but node 5 left should become node 4. Node 4's left child should become node 3. All right, to pick that up. A is going to stay on the left of 3. 3 is going to pick up B on its right. So node 3 right should be B. Node 4 still has C on the right. D stays to the right of 5. A stays to the left of 3. So I think those are the only things you have to do. Right, so if I have my nodes labeled according to this symbology, right, N5 left becomes 4. N4 left becomes 3, and 3 right becomes B. So how do we do that in code? Well, exactly the way that we just described it. So N5 is going to be the new root. So the first thing I'm going to do is I'm going to set up temporary variables that point to each of these pieces of our tree. So for example, so I'm starting with just the root of the tree. We're going to call that N5. Right, so N5 is the root of the tree. So I'll set N5 equal to root. D is N5's right child. Right, that's hanging off there on the right. N3 is N5's left child. So I'm picking up N3, I'm calling that N5 left. A should be 3's left child, but I gotta be a little careful here because node 3 could be null, and if node 3 is null and I say A equals N3 left, I'm gonna seg fault. So if N3 is null, I want A to be null, but if N3 is not null, I want A to be N3 left. So I'll do A equals N3 left, and then node 4 is N3 right. And then if N4 is not null, B and C are N4's left and right children. And to minimize the number of ifs, I actually started off by initializing all of these things to be null. And then, you know, if N3 is null, for example, none of these assignments take place. But since I initialized A and N4 and B and C to be null, they'll still be null. So that's just avoiding having a lot of overly complex logic. And you can see I wrote this kind of brainlessly, right? For example, I initialize N5 to null, and then down here I immediately set N5 equal to root. So this statement is totally superfluous, right? But I wanted it in there. Because when I was writing this, what I was thinking was, let's set everything to null, and then change it to non-null values as possible, as appropriate based on our tree. Now I could have said, oh, but I know I'm always going to do this assignment, and I'm always going to do this assignment and this, so I'm not going to bother putting those in. A big goal when I'm writing code is to try to minimize my headaches down the road. And so, yeah, I've got 3 assignments here that I could get rid of, and I could go back and get rid of them, but it maintains a sort of uniform way that this algorithm was implemented, which was start off with everything null and now assign things as possible. And yeah, definitely always initialize your variables. And so I'm avoiding the possibility that I didn't initialize something. Cool, glad you got that. All right, so I name my temporaries according to this picture, and now we need to do these adjustments. Well, I want n5 left to be n4. How do I do that? n5 arrow left equals n4. That's all it takes. And I want to do n4 left is n3 and n3 right is b, but I want to make sure that I don't do that if these nodes don't exist. So if n4 is not null, then I'll set n4 left to n3, and I'll set n3, sorry, this should be n4 right, should be C. Oh, yeah. N3 right equals B, that comes down here. But again, make sure that N3 is not null before you try to use its right child. So if N3 is not null, N3 right equals B. And then we return the root of the tree, which is N5. So this is a classic example when working with data structures, right? This code is not long, right? It fits on half a screen. And the algorithm is pretty straightforward to describe in pictures, right? We're just taking this and moving it up there and bringing this down here and flipping that over to be on the right. But there's so much going on in here, right? And if there's one thing wrong, if I had done N3 instead of N4, I'm never going to find it, right? I could GDB this till I'm blue in the face, but unless I really understand how an AVL rebalance is supposed to work, I would never find that bug, right? So this is one of the few cases where if this did not work, I would basically rip all the wires out of the proto board and start over again, right? I would probably just go back and I would rewrite this section of code. Because it's small enough, it's not 1,000 lines of code, right? It's small enough to do that. And I really just wanted to read this algorithm, read the steps of this, and write code corresponding to each step. Right? So it's like trying to tell somebody, you know, a 20-digit security code over the phone. If anything goes wrong, go back and start from the beginning. Don't say, you know, no, that 7.5 was actually a 65, right? Sometimes it's easier to start over. Now, I almost always tell students don't do that. If you have a bug, try to find what the bug is, right? Sometimes that's not the best plan for me, right? But honestly, you know, I wrote this without really understanding all the details of how this works. And you don't have to understand how an algorithm works to implement it. Let's see, can we get a copy? Yeah, so actually I was looking for this morning, and if you go to AVL tree balancing and do an image search, you'll find it right here. And I got it originally from Wikipedia, and it doesn't seem to be on there anymore. They've modified it. Yeah, I looked for like 20 minutes before I thought of it this morning, so don't feel bad. But anyway, some people still preserve this picture, and to me, this is a really nice picture. Plus, it's, you know, in color on the web, so that helps. Yeah, definitely don't try to memorize this. Although after a few years of doing it, you almost get it memorized. But not quite. All right. So this is pretty typical for data structure code, right? It's really it's taking an algorithm and converting it into a series of steps, and that's a pretty straightforward process. And so to do the left case, Hold on a second, because I think I have maintenance knocking at the door. Hello. Macias, yeah. Yep. Yep. Awesome. Thank you. Thank you. Wow, that's shocking. Yeah, that's my new Z80 boards from DHL, which I ordered like 10 minutes ago, and they already got here from China. So this is typical of taking an algorithm and converting it into code, and one of the keys here is making good use of temporary variables. And we did this with deletion, right? Sort of this idea of have a largest node and have the parent of that largest node, and then we could do the weird steps of moving the largest to the root and having the parent adopt the root's left child and all of that stuff, right? By just making statements that look, like this or that. And so none of this code is terribly difficult to write. Very difficult to debug if there's bugs. But, left case, we basically want to change 4 to be the root. Everything on the left remains the same, but 4's right child becomes 5, and 5 picks up C, and that's exactly what happens here, right? And 4 becomes the new root, so we return that, and N5's left child becomes C, so it picks up 4's right child. So that happens right there. And N4 picks up N5 as its right child, and then we return N4 as the new root. And so how this fits into the whole scheme of things, that's the other interesting part. So remember, when we do our insert, we do something like, root right equals add root right new number. And this call to add will, perhaps look at the left subtree of that root and insert something into it. And so as we're going through, right, when we start off with this is our root, and we want to add 199, well, our recursion is going to basically say, let's add 199 to this tree, let's add 199 to that tree, let's add 199 to, this empty tree, which gets back, a tree with 199 and makes that the right child of this root, and so on. And we don't explicitly have to start from that 199 and move up and look for an imbalance point. When we make our recursive calls, we kind of wind our way down the tree to a leaf. When we come out of those recursive calls, we're in effect moving back up from that insertion point to the original root. And so yeah, each time that so recursive calls are coming down to a leaf node. When we come out of the recursive calls, we end up basically moving back up to the original root. And so yeah, this is this is called, for example, after you do the insertion on the right or on the left, you call your adjust. And initially, if my tree looked like just this one node and I insert a 199, it's going to go to the right here, and I'm going to try to do my adjustment on this tree's root, right? And there's no adjustment to be made. But that call to insert 199 into this tree was made because I was trying to insert into this tree. And I said, well, 199 is bigger than 75, so let's insert into the right and then make the right subtree of 75 the result of that insert. and then the adjustment I call will be done on this 75 node. And that insert into this tree happened because I originally said let's insert into this full tree, and since 199 was bigger than 17, I made a recursive call which said insert 199 into this tree, and then make 17's right subtree equal to that result, and then I'll call adjust on this 17. So in a sense, this is being run recursively on every node from the node you inserted up to the original root. But we're not explicitly doing that. It's happening basically as the recursion unwinds. And that's really weird, right? That may not make sense at first glance. But it works, which is kind of cool. All right, so we are out of time. I'll talk really briefly about red-black trees tomorrow, but mostly I want to spend the next day and a half, 2 days reviewing and just kind of answering any final questions. If I can get through PA5 grading today, which I probably won't, we can talk about that tomorrow, and we'll just kind of wind up the course over the next 2 days. So have a good one. I will see you next time. Thank you.